Welcome. My name is Magnus Long, and I will be presenting some work we've done with a quite thick title called Optimal Stateless Model Checking for Reads from Equivalence under Sequential Consistency. Now, my goal is that after this talk, you will understand exactly what this means. Right. So, some background. Stateless model checking. So I will start by giving you an outline of the talk, so that those of you who would rather read your email will, get a 2-minute summary, and then you can go on with your day. Stateless model checking. So it's the same thing that Andreas was working on. It is we take as input a terminating current program with fixed input. And we want to find out if there are any errors in this program. So those errors could be race conditions, deadlocks, assertion violations, segmentation faults, etc. And we want to do so in an exhaustive way, which means that if testing terminates, we want to have a guarantee that these errors do not exist in this program. Typically, you solve this with dynamic partial order reduction, which is based on enumerating the orderings of dependent events. However, we can make this even faster by only considering the association between read and write events, the so-called reads from equivalence, which I will explain later. We will introduce an algorithm called reads from SMC that does optimal stateless model checking for the sequential consistency memory model, and is also efficient in practice. And we will present an implementation of this algorithm along with benchmarks that show that this algorithm keeps up with state-of-the-art tools in every benchmark, and in several it outperforms them exponentially. Okay, let's dive in. So, right. The premise is we want to analyze terminating current programs with fixed input. A naive way to do this could be to try all possible ways to schedule the program, but of course this gives an combinatorial explosion of schedules. So partial order reduction solves this by only considering dependent events. So for example, if two statements of the program access the same variable, and at least one is a write, they are dependent because they do not commute. So this gives us a partitioning of all schedules into equivalence classes. We call them Mazurkiewicz traces. And stateless model checking algorithms like DPR executes the program several times to cover all traces and then find all your bugs. So let me give you an example. Here we have a program of 2 threads, P and Q, and one shared variable X. Both threads P and Q first write a value to X, and then read X into a register A and B respectively. And then at the end of the program, we have some assertion. Now, if we look at this program, there are we can think about the different behaviors the program might have by thinking about what values the reads can take. So, for example, one behavior is that both reads take the value of the write from P. Another behavior is that both reads take the value of the write in Q. So here we have graphs of the program where the green arrows denote which reads which write. And then we could have a behavior where both threads read their own writes. And finally, we might think we have a behavior where both threads read each other's writes. But actually, this behavior is not consistent with the memory model. So this is not possible under sequential consistency. And the way we can see that is that if we look at this read, in order for this one to get the value from the write of Q, it must be the case that let's see, the write to from its own thread happens first. But respectively, if we look at this read, in order for it to read the value from P's write, the write from Q needs to happen first. So we get a cyclic dependency of which write must happen first. So this behavior is not consistent. So we have three behaviors of this program. But actually, partial order reduction that considers these Mazurkiewicz traces has this notion of dependency between events, right? And actually, we might see that these two events, the read of the first thread and the write of the second thread, are dependent with each other because they touch the same variable. So this gives us a fourth equivalence class if we use this partitioning. So these partitionings are called Mazurkiewicz traces, and is what DPR typically uses. However, what we would like to do is to not consider these orderings because as far as the reads are concerned, these two behaviors are the same, right? So we would like to be able to do this, where we only have three behaviors, three equivalence classes. So we will call these equivalence classes reads from traces because they only respect this reads from relation. The problem statement is, can we define an optimal algorithm to explore these reads from traces? Optimal is a bit of a technical word in the land of stateless model checking. And it means that a tool that explores these equivalence classes only ever executes the program once and doesn't even begin to explore the program more than one time per equivalence class. We have algorithms that do this for RF traces for weaker memory models, such as release acquire, which is implemented in a tool called Tracer by Abdullah et al. We also have some algorithms for SC, for example, RCMC and DCDPR, which is actually the paper that defined this equivalence, although they called it observational equivalence. However, these implementations are not optimal. So there are cases that are not so rare, in which there are a reasonable number of equivalence classes, but the tools explore an exponentially larger amount of actual executions to cover the entire space. So why is it so hard to do an optimal algorithm for SE? The intuition is a bit difficult, but there is a complexity result which says that the consistency of a reads from trace is NP hard under the sequential consistency memory model from Gibbons and Korak. Our contribution is, in order to solve this problem, we propose a polynomial time heuristic for SE consistency based on a concept called saturation. Now, this is the same as used in the Tracer paper for release acquire, but a bit extended. And we also propose a complete decision procedure for SE consistency, a new one, which has the property that it's polynomial time when the number of threads is fixed. And on top of this, we build an optimal algorithm that explores RF equivalence. And we have an implementation of this in Needhook. So let's talk about this saturation business. So in sequential consistency, the way to know that a trace is consistent is that we need a total ordering of the writes to each thread, to each variable, called the coherence order. And this one should have the property that each read in the execution reads the most recent write. This is also the intuition behind the sequential consistency memory model, that it's defined on interleavings of thread executions. And the reads from relation actually implies part of this coherence order in the sense that some of the orderings are forced in all linearizations that have this reads from relation. And saturation is an attempt to try and infer all of these implied coherence orders. So let me walk you through an example. So saturation is basically based on converting this idea of consistency into inference rules to enforce that each read reads the most recent write to the same variable. The first rule is that when you have a write before a read, it must also be before the write that read reads. So let me show you an example. We have this program from before, the running example I have. And I will add some more edges to the graph because we need to preserve program order, because we cannot reorder the steps of a thread. Let's focus on the read to register B. So B reads its value from P's write, but it also has a write that happens before it, that is its own write. So this inference rule says that these two writes must be ordered this way, because if they happen in the other order, B would read the write of 2 and not the write of 1. And we have a second rule that says if a write happen after another write, then it must also be ordered after its read. So this is also easier to see in an example. We had this trace from before. If we say that we have that the two writes are ordered like this, for whatever reason, say that the program continues and we infer this ordering, then we see that these two writes are now ordered. So we have a write that happens after another write. And then the rule says that we must complete, we look at this part of the program, and the write must, all the reads of the write must finish before we're allowed to overwrite that value. So these are fairly intuitive. However, in the case where we didn't have an ordering between the writes in this case, saturation will actually not do anything, because neither of the rules are applicable. So this graph could describe this execution as much as this execution, right? Whichever order they come. So this is a problem. And why is it a problem? It's a problem because we don't have a total coherence order, and so we do not know for sure whether the execution is actually consistent. It might be that this is impossible. There is no interleaving that yields this trace. We just don't know. So how do we fix this? Simple. We extend the saturation with a heuristic, and the heuristic is not so difficult. So we start with a saturated graph, this one we had here before. And then we take the earliest pair of writes that are not ordered, so these two, for example, and we guess their order, because if saturation didn't infer order, maybe the order doesn't matter, that it's possible in either way, or maybe we just didn't know. So we will guess that they are ordered this way, because in the previous execution of the program, they were ordered this way. And this trace will in that case, only be a small tweak of the previous trace. So the intuition is that it's likely that this is an ordering that satisfies consistency in this case again. And now, after you've guessed one edge, you keep saturating. So in this case, we can now infer the edge that we had before. And then you repeat this until you have total coherence order. And if you can do that, and saturation doesn't find that your execution is inconsistent, then you win. We have proven this to be SE consistent. And if it doesn't, then we have a problem, because we don't know if we guessed wrong or if this is actually an inconsistent execution. However, in practice, we found out, we tried this, implemented this heuristic and tried it on a large swath of benchmarks. And we find out that in practice, it does not fail. So this heuristic, whenever a program is inconsistent, saturation is enough. And when a program is consistent, the guesses will always be in a possible way. To the results. We have implemented this algorithm in a new mode of the nidhook tool. We will call it nidhook RF in the paper and in the tables. And we've evaluated it on a number of benchmarks. So let's start with some standard benchmarks for this type of algorithms. These are from SVComp. And this particular benchmark has the property that it has the same number of Mazurkiewicz traces as it has reads from traces. So in this particular benchmark, the improvement we have made does not help you, but we can see here on the results that our tool is not slower by more than a small constant factor than other state-of-the-art tools. And we can also see that for some tools, such as the CDPR in this case, that are not optimal, we can see that even though this is a relatively easy benchmark, whatever easy means, by virtue of not being optimal, it just so happens for this particular benchmark that they explode and take a really long time. So this motivates why it's desirable to have an optimal algorithm, because we can give this guarantee that we are never worse by more than a small constant factor than anything else. Here's another benchmark from SVComp, where the number of Mazurkiewicz traces are significantly more than the reads from traces. So in this benchmark, it really pays off to be checking under reads from checking reads from traces, and we have again. So here we have the observers mode of nidhook. We saw it named nidhook star in the previous talk, which is the only mode of nidhook that can keep up with this benchmark prior to this new work. And RCMC is now split into two columns because it has one mode that explores Mazurkiewicz traces and one that explores reads from traces. And we can see that tools that explore Mazurkiewicz traces are hopelessly behind on this benchmark. And that in this benchmark, RCMC with RF traces is the fastest, but not faster than by a small constant factor than our new technique. And here we have another benchmark. This one is not from SVComp, but it is from the DCDPR paper, and it is some code or it's a translation of code from the JVM, some tricky locking code inside, reproducing a bug that has existed in the past. Now this is the fixed version of the code, so the benchmark, and this is useful for benchmarking because we can then it's not based on luck on how fast the tool is. All tools have to explore all equivalence classes, and we can see again we're not the fastest, but no slower than by a small constant factor. Now we have some other benchmarks. Here's a case study from something called the Systematic Concurrency Testing Benchmark Suite. And this is a relatively challenging benchmark for SMC algorithms. And here we can see that our technique performs very well on this. So in this table, unlike the previous tables, we are showing the number of executions, the number of traces in the case of optimal tools. And it's very good. But this is only until finding a bug. So it could be the case that we are simply lucky to get this number. However, by fixing the bug, by commenting out the assertion, and we do this just to see the number of total equivalence classes in this program, we can verify that our tool is not actually lucky, but it's simply a result of having a very coarse partitioning and an optimal algorithm. So here we're able to check in a minute what other tools needs at least days, if not completely months, to check. And I have another thingy, but I will skip it in interest of time. So we have presented reads from SNC, a new algorithm that is optimal for SC. It's based on a heuristic that turns out to be very efficient in practice. And it's backed by a novel decision procedure that is polynomial time if the number of threads are fixed. And we've implemented this in the NetHook tool. Thank you.
So again, we have time for one question. Yeah? You.
Yeah, so thanks. Just a quick comment.